Yes, welcome everyone to geohug. So before we kick off today's session, I'd just like to take this time to acknowledge the traditional lands which we're all coming from today. And I'd like to pay my respects to the elders past, present and future. So I'm so excited to have Danae Voormeij with us today. So Danae is an exploration geologist with expertise in gold deposits. So she's got 20 years of international field experience managing exploration teams in remote locations and new geological frontiers. So she's explored for orogenic gold, gold-rich VMS styles, and orogenic copper mineralized systems across the African continent, and has held positions of chief geologist, exploration manager, and VP of exploration. So with her expertise, I'm so looking forward to hearing from her today about exploring for gold and copper in areas with tropical laterite cover. So it is going to be a great session. The chat is apparently still not working, so keep using the Q&A. Any questions, any discussion, we'll open up the floor at the end. And yes, thank you so much, Danae, for joining. It's wonderful having you.
Thank you, Jessica, and thank you for the lovely introduction. As the title states, this talks about gold and copper exploration in areas with tropical laterite. Thank you again, Jessica, for the introduction and for having me on the GeoHug platform. And hello to everybody who's joined in today. Thanks for coming. Most of the information that I cover in this talk is also in a book that I wrote, and that's freely available on open access on researchgate.net. So just keep that in mind. You can always come back to this talk and view this link. All right, so let's go through the outline so you know what's coming up. In this talk, you're going to learn about regolith, and in particular, the laterite regolith, which is the dominant soil type at tropical latitudes. And laterite development is largely controlled by climate. I'm going to put on my little laser thing there. Here we go. And it's largely controlled by climate. So we're going to be covering 3 main tropical climates. And then we're going to go and look at all the zones of the laterite regolith, and you'll be well familiar with everything you see here in this picture, for example. Then we'll move on to Supergene gold formation and how it's formed, how gold is dispersed as this mushroom halo within the laterite regolith. We'll look at titanium as a soil geochemistry pathfinder for orogenic gold and orogenic copper. I'll go through soil sampling procedures once again, and the talk will finish with artisanal gold mining styles and how we can learn from them and use them as vectors towards exploring for gold deposits. So let's get started. What is regolith? Regolith is the entire cover that overlies bedrock, and that includes the organic materials, the vegetation, your topsoil, subsoil, and your decomposed rock, but also boulders and dirt and transported materials, glacial tills, sand, desert, volcanic ash, they're all part of the regolith. Let's look at regolith in space. On the moon, regolith forms as a result of billions of years of meteorite impacts. And the very first famous footstep on the moon was done in lunar regolith. The regolith blankets the moon, and estimates are about 5 to 15 meters in thickness. And what's interesting is that the regolith on the moon, it's made of glass and mineral particles, but also lithic fragments. And the regolith collected over the mares that are more basaltic rich have more basaltic fragments, whereas the regolith that's collected away from the mares have less basaltic fragments. So the regolith on the moon is residual, which we will cover in more detail in a bit. Let's look now back at regolith on Earth, pulling you back down to Earth. All right. On Earth, regolith is a product of weather. We don't get the meteorite impacts, hopefully. In this talk, we're going to focus on the tropics. And the tropics is the area centered on the equator and bound to the north by the Tropic of Cancer and bound to the south by the Tropic of Capricorn, hence the name the tropics. In the tropics, there's lots of high heat and humidity, and that causes the bedrock to weather very deeply. In fact, the global distribution of deeply weathered regolith shows that 1/3 of the world's landmass is covered in laterite, deep tropical weathering. So this tropical regolith, if we look at the surface of it, here's again our organic layer and our topsoil, And then we have the B soil named Laterite. That's because over geologic time, this weathering front becomes layered, and you're going to be learning about these different zones of the Laterite regolith. It's important to learn about the regolith because the regolith is what stands between you and the metal deposit in the bedrock at depth. So it's good to know your regolith in your project area. In composition, Laterite is high in iron and aluminum oxides. So here's a soil pit. You can see your O soil, your A soil, and then your exposed laterite. When you think of or watch a movie that takes place in Central Africa, you see the Jeep driving across the road. It's a red road with red dust. And what does that mean? That's actually a laterite exposure. So in this case, the vegetation and the topsoil has been removed to make the road, and you're looking at laterite. Laterite doesn't always have to be red. It can be more brown, it can be gray, but it's dominantly in red in color. Now the laterite's very clay rich. So when you get stuck in the mud in the tropics, you're getting stuck in laterite. It's very, especially after a rainy season or a rainy day, these are very common when you're working in the tropics that you get stuck. So it's good to have a winch. There's a winch on the front of this vehicle and here as well. And you can see we use the ropes to get ourselves up the hill and through, but also we use the winch. You can see the winch coming through to help other people through so that we may pass. So it's good to have a winch on your truck. Laterite regolith development. It depends mostly on temperature and rainfall, and in particular seasonality of this rainfall. There are many other conditions, EH/pH conditions, presence of sulfides that create a more acidic environment, parent rock composition, the porosity, structures, and permeability, as well as tectonic shifting, uplift, and of course time. It's estimated that laterite regolith development takes about, is at a rate of about 1 meter or 1 meter per 10 million years, because you got to take into account the erosion. If we look here on this image on the right, you can see that both those rocks have been exposed to laterite development, but the granite has a very thin soil cover and doesn't have much laterite development, whereas the dolerite is far more susceptible to deep laterite development. So if it takes 1 million years to develop it, then how come this volcanic ash in Hawaii, which is only 16 to 30,000 years old, how does it have such a deep laterite development? Well, let's take a look. We've got the weather there. So we have 1,300 meters annual rainfall that puts it in a tropical savanna climate. And the ash is about 3 to 5 meters thick in places. The ash is composed of natural glass, pumice, and olivine crystals that are loosely packed together, and fragments have small bubble holes. So what that means is it's extremely permeable with unstable materials, and it can hold moisture. And it's said that these soils, in fact, are almost always moist. So hence the deep laterite development on such a young rock or volcanic ash flow. So let's look at these climates. The tropics experience seasonality. I was surprised when I found out, but they certainly do. And you can tell by looking at the rainfall. But let's first look at the 3 tropical moist climates. So we have the AF, which is the rainforest. We have the AM, which is tropical monsoon. And then the AW, which is the tropical savanna. And you can see the rainforest centered here around the Amazon, around the Congo, and in Indonesia. Whereas the monsoon is more along the trade winds. And then the savanna is in sub-Saharan and in parts of Brazil, for example. So we're going to briefly look at each of these. So here's the tropical rainforest climate known as AF. And it's an expression, this climate's expressed through its vegetation. So it's densely forested. It's usually very dark in the tropical rainforest. There's very little light that enters through this canopy. There are very tall trees and a lot of rain. So we have a high rainfall on average 1,800 to 2,500 millimeters per year. To put that into perspective, North Vancouver gets 2,400 millimeters per year. And that's because we're, Vancouver climate is a rainforest climate, it's just temperate. This is rainfall data collected from Dugby in West Africa in Liberia. And what you can see a wet season followed by a dry season, and then another wet season followed by a dry season. But throughout the year, there's always some rainfall, so it's never completely dry, but there certainly is a seasonality that happens. Let's look at this tropical monsoon climate. Again, high rainfall, typically along trade wind coast. But when we look at the rainfall data, we see one wet season and one dry season. It's quite dry, but not completely dry. You can see a more open canopy, there's more light that comes through. And moving on to tropical savanna. So tropical savanna is the driest, of course, of the three, has a lot less rain and has a very pronounced dry season. So here you can see you can have periods of drought. And grasses dominate, trees have really small leaves, a lot of sun reaches the ground, and plants have thorns and such. And so those are the three tropical climates. If you know what your climate is of your project area, you can start planning for your program so much better. You can plan for your camp construction, bridge repairs, transport of samples, when to collect your stream sediments and soil geochemistry surveys, when to target the creeks for bedrock mapping. It's very useful to have a weather station. It can be as simple as something that's like a large test tube that you fix to the deck in your camp. And every morning the security guard comes out there and writes how much water is in there and empties it out. Or it can be a weather station that's highly technical. But in either case, you can get this information. If you're new to your project area and maybe there's a 43101 report written about it, it will often say something about the climate and even about the rainfall. So you can get that information in advance. Quick quiz. Here we go, guys. Pop quiz. In this case, you can't answer directly to us, but you can answer to yourself. How's that? So then I'll post the question and then you can think about it. And on the next slide, we'll go through the answers. Let's see if you paid attention. Which tropical climate has 2 dry seasons and 2 wet seasons? Which rock type weathers faster, deeper, volcanic ash or andesite? The tropics is centered on the Tropic of Cancer, true or false? What's a soil called that overlies laterite? Let's see who paid attention, even though we haven't covered the layers yet. Is the desert a type of regolith? And how about glacial till? All right, so let's take a look at the answers. 2 seasons, tropical moist rainforest, AF. The volcanic ash weathers deeper, faster. The tropics is centered on the equator and bound by the 2 tropics. We have an A topsoil, and both of those are regolith. Moving on to the individual zones of the tropical laterite regolith now. And let's look at the term residual. Residual means in place and derived from the same place. That means that these soils are derived for the most part from the underlying bedrock. That's why we want to collect these soil samples and do geochemistry analysis on them, because we want to know what's in the bedrock. We just have that regolith in the way. But there are parts of this regolith that you shouldn't be sampling. Like the mottled zone is highly leached. But the laterite, the B soil, is a very common soil sample in soil geochemistry. Let's look at each of these layers. To begin with, the organic topsoil. It's right beneath the vegetation and it's dark brown to dark gray. And one way to really recognize it is that it has these fine hair-like rootlets in it. And that's because the plants are feeding on the mobile elements that are available to them in the A topsoil. It's silty clay in texture. So you see these lumps in here. If you take those between your fingers, you can crush them. They're not hard. Whereas the laterite will have hard fragments in it. This A soil can get really thick, especially in tropical savanna, and in which case it even differentiates into an upper and a lower A soil, where you have a zone of leaching and lots of rock fragments in here. You can see these rock fragments. And then you have the zone of accumulation at the base in the lower A. And notice again these white hair-like rootlets. And it's clay rich. So that's your better sample if you're targeting A soil. Let's look at laterite next. And here's some examples of regolith profiles from different papers. And first thing from rainforest, tropical rainforest projects. And the first thing you'll notice is that they often don't really describe the topsoil very much, and goes pretty much straight into laterite. And there are a lot of different names given for laterite. Iron-rich crust, nodular horizon, nodular layer, and so forth. So let's look again at the laterite here. So we have a nice thick layer of laterite here. And within the laterite, there are resistate minerals that are left over. So this is this residual rind of the rock weathering and laterite lowering. So you get erosion and washing away of the mobile and disintegrated elements. And then you have this resistate left over in your laterite. There's absolutely no rock texture left in the laterite. It's hard to try and identify the rock type based on looking at laterite. This map here shows a laterite distribution. You can see it's mostly centered around the equator there within the tropics. Stone lines, and stone lines are a really interesting part of the laterite regolith and are often contested as being transported, but there's lots of evidence for them being residual. So I think they're just a bit of both. It depends on your environment. If you're in an environment that's conducive to sheet wash and your surface topsoil's washed away and you just have laterite at surface and you have sheet wash of quartz vein fragments washing across the landscape, those end up settling and also form a stone layer. But in general, stone layers are thought to be residual and be formed as the result of quartz veins breaking down, and those parts being resistant, they end up forming a stone line. Now here's some interesting parts that I pulled out of a stone line in Madagascar. And you can see artifacts and entire crystals, including dipyramid quartz crystals, that were just the resistate in the laterite, and they end up settling into a stone line. But as I said, they can also be transported, so it really just depends on your environment. It's a good time now to look at the hydrology briefly here. On the right side, you can see that laterite regolith again. We've got soil and laterite, and then what's called the mottled zone. And the mottled zone is sitting right at the water table. So during a rainy season, this fills right up. This is saturated during the rainy season, and during the dry season, it draws all the way down. And that makes it really porous because that drawdown leaches more strongly and you get a faster flow. And this image here shows the mottled clay layer here is highly porous, more than the rest of the regolith profile. So the mottled zone marks the water table. So you get your rainwater coming in, infiltrating the soil through the laterite into the water table. This mottled zone is therefore highly leached, and it's called mottled because you end up with these mottles, these streaks of these iron oxyhydroxides against this very leached background. Again, it's extremely difficult to try and figure out what your primary rock is when you're looking at the mottled zone. And areas that experience extreme drought or a really strong groundwater flow will have a much thicker mottled zone. But you can have a laterite regolith that hardly marks that mottled zone at all, and it's probably because the climate's more steady and has less seasonality. On to saprolite, and now we're working our way down this regolith profile towards the bedrock. And the saprolite, you can see, is more competent. Excuse me. And it preserves all of the textures of the bedrock at depth. So you can map saprolite, you can sample saprolite. It's the same as sampling at depth. And this is what you want to reach when you are trenching. But road cuts are fabulous to sample from as well. In this case, it was so competent, I could create these pillars with the trenching so we could get a nice 3D mapping of structures in there. This is in Suriname, in Dutch Guyana by the Amazon, and it's a high humidity, tropical rainforest environment. And this is at Gross Roosevelt. You can see the laterite cap at the top and then some mottled zone, and all of this is saprolite. It's so soft you can push your finger into it. And the colors are just gorgeous. You get all these pinks and purples from the oxidation of the iron-rich minerals. And even more beautiful, as you can see, these ductile deformed quartz veins. These are gold-bearing quartz veins, perfectly preserved within the saprolite. At Gross Roosevelt, the saprolite reaches 150 meters in depth. And the first few years of mining, there was no crusher at the mine. It wasn't necessary. Now onto saprock. We're almost now at this weathering front, and saprock can't be broken in the hand. You could cut this with a knife with a blade easily, but you can't push your finger into it. And it retains all of the original rock fabric. And saprock is often exposed in streams and gullies because the top of the regolith has eroded away. So it's a good example of where you want to wait for the dry season to do your mapping of your gullies and creeks to get down to that saprock. Core stones are an interesting feature, but easy to understand. This is all one rock type, and core stones are simply less weathered pieces within a more weathered matrix. So these are really from the next layer in the horizon further below, if that makes sense. But you can see all the structures perfectly preserved in saprock and in the saprolite, but it just looks like they're different rocks, but it's actually the exact same rock. So that's something to keep in mind when you're drilling through this. You can imagine you might think you're looking at different rock types, and just keep that in mind, that you can get core stones floating. And then we reach the weathering front. See, we went through all of those layers now. And then we reach the weathering front, and it's the contact between the fresh rock and the weathered rock. And that contact can be really sharp, like in a basalt, or diffuse, like in a sedimentary rock or sandstone. Okay, so this is like your alphabet now. Now that you know your zones of the laterite regolith, now we can get into the real good action. Keep in mind that there are many variations in laterite regolith. You can have zones that are emitted, you can have zones that are repeated. You can have gravelly laterite, you can have a massive laterite, you can have massive Duricrust, which we'll talk about next. Yes, you can have different types of laterite. Keep that in mind. Also, the mottled zone can have models that are elongate and that even harden and become what's called indurated. And over time, they would even fuse to the bottom of what's called a Duricrust. And that happens when laterite dries out. So some of you may have seen some Duricrust blocks in your project areas. They rarely cover a whole layer because they're part of an ancient landscape from a time when that project area was in a tropical moist climate. And then it moved out of it, either the climate changed or tectonic plate shift. And then that laterite dried out and became Duricrust. And that Duricrust is really hard and can hit it with the hammer. You can hear sort of metallic sound almost. It can be hard to break up. And they typically cap the landscape. So here you can see by Chardon, a recent paper where they figured out that these caps are dominant on pediments, and they're part of ancient landscapes, of several different types of ancient landscapes. Ferricretes, I know these terms are often interchanged, but ferricretes are Duricrusts that incorporate transport materials, and that's how to classify them. Tectonic plate shifting. So first, this part of Africa was on the equator, and then it shifted northwards, and that's where you get all this Duricrust capping. Duricrust is therefore found capping plateau in sub-Saharan Africa, but it's also a common feature of the regolith in Western Australia. You can get Duricrust dismantling. So now imagine if these project areas experience tropical moist climate again, and that does happen. Climate changes over time. Then that Duricrust will break down again at the resulting in the formation of these nodules. So that's what these nodules look like. I think they're really cool. They have a nice desert varnish on them. I have some here. They are metallic. Did everybody hear that? They're very metallic-y, and they're formed as a result of that environment going into a more humid area. You can also have pissoliths, and also known as lag, and that's a result of laterite being exposed to droughts and a lot of sunshine, and you get these pellet-sized, pea-sized lithic fragments. Nodules, pissoliths, and pissolith concretions, they're all pretty much made of goethite. Here I scratched it a bit. You can see the yellow inside of the goethite. And they make for great road surface material. So if they're in your area, you may want to consider using that to armor your road a bit against that laterite mud. Quick quiz. All right, everybody ready? I hope you paid attention. Laterite regolith can get up to 150 meters deep, true or false? Duricrust forms when laterite dries out, true or false? Nodules and pissoliths are good sample media, true or false? Which is the better soil sampling medium, A or B? Answers, true. Gross Roosevelt is an excellent example of showing extreme depths of laterite regolith. True, Duricrust forms when laterite dries out. False, you don't want to be sampling the nodules and pissolith. In fact, you don't even want to be sampling the Duricrust if you can help it. You want to get to the laterite. And I appreciate that there are areas where all you have is pissolithic lag or nodules, and then I guess if that's all you have, but they don't make for good sampling media, I don't think. And which is the best soil sampling medium? It really depends on your program. But in general, it's the B laterite soil. Remember that the B laterite is pretty much everywhere, but that A soil can be less developed or stripped by erosion. The important part is to be consistent in sampling the same soil type, rather than consisting depth, which is what a lot of programs do. They say, okay, let's sample between at 18 centimeters depth, because they hope to be in that B soil laterite. But you want to follow it throughout the landscape because there are areas where it's thicker and thinner. Gossans. Gossans result from the oxidation of sulfide-rich vein systems or deposits. So depending on your mineralization style, if you have a lot of sulfides in your system, you can develop a gossan at surface. Yes, they can occur in temperate climates as well as in the tropics, but in the tropics, they'll occur at the water table, at the base of the laterite. And what can happen over time is all of that above can erode away, and you can have an exposed gossan sitting in your laterite. And of course, they're great markers for exploration of the ore deposits. So gossan, from fresh rock towards the gossan, is what happens in the mineralized system is you're gradually losing sulfur from your sulfides, you're losing sulfur and the minerals are changing, and you end up with the gossan that's quite depleted in some elements, and then can be enriched in, say, gold and silver. How to recognize a gossan, especially if it's all red and such, and how does it look different from a Duricrust or laterite when you're in the field? So it's a really important question, because if you're not familiar with laterite or Duricrust and you're on your project site, you may think you're looking at gossan. So how to distinguish between those is that gossans have what's called boxwork, and it shows where the minerals, the sulfides were before, and then they're weathered out. So you can see here little squares of the boxwork of pyrite. You can see really spongy texture that's left over in the Gossan. And copper minerals don't tend to do pseudomorphs. They tend to make supergene chalcocite, but you will end up with some copper oxides in your Gossan. For more information on that, please refer to this great book, and it also covers a lot of different sulfide pseudomorphs. Quick quiz. I hope everybody's ready. That was really fast, but you know, keep you on your toes. Which two are the gossans? Ready? Boxwork textures, lots of porosity, copper oxides. These are all indicators of a gossan. And yes, there's some porosity here, but you won't see the little cubes inside. All right, another thing you can do with your project area is you can figure out what paleoclimatic history it went through. So you may have heard of Chris Scotise's PaleoMap projects in the past. You can go to his website. Here's the link. And in the past, he made these cool videos where you can see tectonic shifts happening in videos. And that was a big deal like 20 years ago. But since then, he's done more work, including work on paleoclimates using fossils of crocodiles and fossils of palm trees. And with that, he's able to see over time, so this is for say 100 million years ago, but he moves through time, and you can actually see where your project area was over time. And with that, you can predict what type of regolith you may be encountering in your project area, which can be very helpful. For example, you look at Australia here, it underwent a number of tropical humid climate conditions and tectonic uplift, and got a really deep regolith. Oh, sorry. And then it was stable since the Phanerozoic, and that has left this really deep regolith on most of Western Australia. And here you can see an example. Now you are more familiar with the regolith profiles. You can interpret them. So here we have the lag. Those are those pisolists on surface. There's your soil, which is rarely described in detail, but that's your A soil. There's your laterite, which is your B soil, and the mottled zone. So we know now that that's your water table right here, right? Here are your models. There's a clay zone because that really deep regolith, remember we talked about extreme droughts, then you end up with a much bigger mottled zone, and you don't want to be sampling from any of this. It's highly leached. And here are those core stones. If we look at the topography in the age of landscapes, for example, back to Suriname, Dutch Guyana, this is Paleoproterozoic age. These are really old rocks, and you have a really lowered landscape. You can see there's a dike running through here. But overall, it's very low, and erosion then is slow and inefficient, and you get that really deep regolith. And complete. So wherever you go, you will mostly see the intact regolith profile. Now here, if we look at Papua New Guinea, at West New Britain, these are younger rocks. They're deeply incised, and the rate of physical erosion exceeds that of chemical weathering. And so when you're working in a project area like this, you will end up faced with different regolith profiles that are truncated. And you won't have complete regolith profiles in those cases, and that's something to be aware of. Right, let's look at supergene gold formation. Here we go. When the gold-bearing vein is exposed at surface, you get mechanical and chemical dispersion of the gold particles. And for all of the chemistry behind supergene gold formation and all the chemistry behind laterite formation, you can refer to my book. I'm not bringing that chemistry into this talk. This is more of a high-level talk, and I want everybody to follow it. Now, supergene gold enrichment is especially prominent in the tropical laterite regolith. This is what it looks like. They're nuggets. It's pure gold. It has an extremely high fineness. That's because while it's being remobilized in the upper surface, it actually loses its alloys, and you get a release of what it's normally alloyed with. Gold's alloyed with silver, copper, tellurium, bismuth. It loses that, and not only does it lose that, it also searches each other out and agglomerates and forms nuggets. And you can have dendritic form, you can have large nugget forms like in Australia, and they're very high fineness of gold, high purity. Supergene gold forms at the base of the laterite in a general sense. If you are in a more arid climate or your project area has moved to a more arid climate, it can be drawn down and you can end up with supergene gold formation in your saprolite. But in general, it forms at the water table at that time, which is at the base of the laterite. But again, like I said, if that project area moves into an arid environment, that can be drawn down further and deeper down. This is the famous mushroom dispersal pattern that's so often mentioned in the tropics that you must be aware of when you do your soil sampling and you look at your results, because you get this very large halo and how to find your primary deposit within it. And it's termed mushroom because, as you can see, there's a mushroom cap of fine gold particles, and then the stalk of the mushroom, and that's sort of the stalk of some gold dispersion in and around the system, but there's much more gold dispersed near the top of the system. And that was first recognized in the Ivory Coast in the 1960s. This effect, of course, is strongest, as we're saying, along the base of the laterite. So here's a diagram I made to illustrate orogenic gold, and here in the footwall I gave it some sulfide ore, so it's got a Gossan sitting in there as well, and here you have this mushroom dispersal halo, and here's the water table again and your deep weathering front that gets drawn down mostly by the acid created from your sulfides breaking down. So that's supergene gold, and your enrichment is sitting right in here. So it's dispersed as a halo, a low-grade halo with an enrichment right at the base of your laterite. If you have major structures, you can draw that front down even deeper. So here, let's look at a low sulfidation epithermal, a diagram I created to illustrate how along that structure you get a really deep drawdown of oxidation, and all the gold within this area then is refined and of a high fineness and highly desirable by mining companies, of course. So you have a sort of a more narrow mushroom dispersal halo. The takeaway here is that the oxidation front follows structures, so it doesn't have to be a very old system to have a major oxide development. So in the tropics, we have high rainfall, high heat, and this equates to an extremely high sediment load. And that's why when you're working in the tropics, you want to do stream geochemical sampling as your first pass. The best time of year for stream sediment sampling is directly after the rainy season, another reason to know your seasonality. Similarly, if there's been a major cyclone, that's a great time to go out and quickly get all your stream sediment samples, because you want that fresh gold being brought nearer to surface and not being settled deep down within the sediments. What you want is 200 micron grain size as your sample, and since you're usually collecting one stream sediment per square kilometer and you're walking a lot, or your team is walking a lot, you want to sieve that down to size so you don't carry huge samples across many kilometers. So that's why you can see the team here with their set of sieves, and they end up with a minus 177 micron sample size. All right, quick quiz. All right, everybody's paying attention still. That's great. This is your claim area. It's a dendritic rectangular hydrology pattern, and that's that lowered landscape classic. Your target is orogenic shear zone hosted gold. You're in a nice tropical rainforest, and there's a high sediment load. It's the month of November. Is it a good time to be stream sediment sampling? Where would you place your first pass sampling stations? Right. So I put them on for you. And what you want to do is you want to, for first pass, you want to get about 1 sample per square kilometer, and you want to sample at the confluences. And then maybe once or twice upstream. That's your first pass. Is November a good month? Yes, absolutely great month, because it's right at the end of the wet season. It's a perfect time to be out there getting these samples. So here, your results are back at Aquaregia Digest, and you've got some nice anomalies in there. And so you want to do your second pass stream sediment sampling now. So what you do is you're going to focus on your anomalous drainage and then take it in steps of 100 meters. Again, the confluences, and upstream every 100 meters you take a sample. And if you were in a hurry, you may even want to start a soil program. All right, speaking of soil sampling, let's do this. We're doing this together. Let's go over soil sampling. What do you do when you reach the site? You've arrived at your sample station, and you're going to start by clearing away the O soil to expose your A soil. This is a geo tool. It's very handy to strip. And the key word here is strip and not dig. So you want to pull back 1 layer at a time and put it on the sheet, and that is your A soil, right? Your top soil, until you reach the top of the laterite. That's your B soil. So here we're looking in a soil pit. Here's A soil. You can see all those white hair-like rootlets sticking out. And this is the laterite. It doesn't look bright red. It's nodular. This is a nodular laterite. And so you've got your A soil, you've got your B soil, you put your ruler in there, you take a photo of the pit. And here again, you've got your A soil. It's not always brown, it can be reddish, but those roots, the roots really give it away. So you got your A soil. This was for demonstration purposes. I did 2 pits side by side here, and you can see this is your laterite. And you always take a photo to show your depth to the laterite sample. What do you do with these samples? Okay, well, you want to know the color, you want to know the texture. You got to put your hand in there and feel it. And you can see these hair-like rootlets again. And here you can see fragments. So if you feel it, these are really hard fragments. And these are clumps that you can break apart with your fingers, and it's silty clay. So that's your A soil, and that's your laterite. I think we've gone through that enough. Now everybody knows how to do soil sample. That's excellent. Let's look at the results from your soil sampling then. So an aureole is a dispersion pattern found within the bedrock, whereas we're looking at the regolith. And in the regolith, the dispersion pattern is called a halo. Here we have a golden soil anomaly that's 1.2 kilometers in length. It's a Birimian hosted, so you see this classic northeast trend. And here's a deposit. It's dipping towards the southeast here, and the daylight's right in here. These soil lines, by the way, they're 250 meters apart, and they are going across the main shear direction, so perpendicular across your shear. You mark off all your artisanal workings that you see along the way or from satellite imagery. Yeah, you want to note your mining activities along the way. So let's look at that in a bit more detail. Here's your golden soil anomaly and all the workings. And this is where it daylights. We knew that afterwards from drilling. So the golden soil anomaly is one thing. What about the rest of your geochemical elements? If we look at silver, we get this incredible halo, right? That's what we were talking about. We get a halo, dispersal halo. We look at tellurium, it has a dispersal halo and this bullseye core. I really like tellurium. I think tellurium is one of the top pathfinders for orogenic gold and probably for other mineral deposits as well. So this core here is greater than 1 ppm tellurium, and then the halo is half a ppm. And if we look at a bunch of elements, you get this lovely donut shape of all these elements that are dispersed, and they're just mobile elements being dispersed outwards, but they surround the deposit and don't really go much further than that. So they've moved out of the deposit in the regolith and then reprecipitated out on the edge. Again, tellurium, this shows a number of examples of tellurium found in soil overlying famous deposits, and always drill your tellurium high. You could actually just go and drill your tellurium high right away if you get your, because there's so little tellurium in the background rocks that if you get tellurium in your geochemistry, it's usually a really good sign, especially if that's what you're targeting in something like orogenic gold. So this halo dispersal pattern, if we were to take a section along here, well, it would look like this. We would have a peak, and here's that deposit again dipping to the southeast. So in section line, the silver shows up as 2 peaks, and it's another good reason to really make sure your soil lines are far enough. I'm known to cut my soil grids pretty tight, as you can see, but you really want to have some of that background so that you can pull out those peaks or your halo. Well, those peaks are also known as rabbit ear peaks. I'm sure you've heard of those before. For those of you who haven't, the halo pattern is the rabbit ear peak in cross section, and so your target is actually sitting right between those 2 peaks. So what's causing that dispersion away from the deposit within the regolith? And that is the acidic cell theory. And the acidic cell theory says if you have a lot of sulfides in your system, they start to oxidize, they create acid. That acid mobilizes elements even more than usual, and they get mobilized away from the system over top in the regolith. And then as that acid no longer has an effect, then they precipitate out again. And so you end up with these halos or rabbit ears. Well, you can do an intense soil geochem survey, and they're pretty pricey these days. I think it's $50, $60 to get a sample done. It sure has inflated. But there is a really inexpensive method to find these acidic cells, and that's Barry Smee's IDH method. And all you need for this is your A soil samples, distilled water, and a beaker. You can use dilute HCl, but you can also use a bottle of table vinegar. Jessica, you could go out into the outback with table vinegar and some water and a pH meter, and you can find a deposit. And this has been proposed by Smee for the last 2 decades, and it works. It works especially well in arid covers. And here's an example of a deposit found in Namibia through 130 meters of cover. And that cover, of course, is regolith. So you can see through regolith because you can find this acidic cell within your regolith. And what this measures really is the buffering capacity, and it's measuring where the calcium has been removed and then reprecipitated into these rabbit ear peaks. What's really cool also is that the rabbit ear peaks can even give an indication to the dip of your system. So if you want to find out more information about that, you can look up Smee online and the IDH method. And what IDH stands for is you take the inverse of the difference of your pH readings before and after you add that drop of acid. Trenching is great to follow up on your soil anomalies. And what do you do when you're trenching? Well, you want to get down to the saprolite. That's really important because you're mapping and sampling. If you're testing for Supergene, you also want to sample along the base of your laterite. Can you spot the trench in this picture? No, that's because it got infilled. That's what you're supposed to do when you're done with your trenches. Keep it nice and clean, keep it nice and tidy when you're done. What to map and what to sample. If you're gonna tell your team, yeah, I want 3 lines of a kilometer each, maybe it's a good idea to get somebody to do some soil pits first and just see how deep that saprolite is sitting before you commit your team to doing massive lines. Only one side of the trench is consistently mapped and sampled. And if you have thick mottled zone in your area, that's really dangerous to trench and excavate, and it carries no value anyway. So you want to get away from that. The saprolite must be reached because that's what you're mapping, that's what you're sampling. Do you think they reached the saprolite in this trench? Take a closer look at that. Well, there's our topsoil. There's the laterite. In this case, the laterite's brown, orange brown, and the saprolite's actually a deep red. It's probably metavolcanic and lots of iron-bearing minerals, resulting in very red saprolite. So yes, they reached the saprolite. This is a great trench, not too deep. Quick quiz. Everybody's doing so great. If your trench doesn't quite reach saprolite within a couple meters, what to do? Well, you can sample laterite instead, dig deeper, move the trench up slope or down slope. You want to move the trench up slope because you want to get maybe towards a bit more of a truncated profile then where you can reach your saprolite faster. Regolith mapping can be hugely beneficial in your interpretation of your soil geochemistry. This is an example here of regolith mapping, and it was done in 3 phases here. What they did is they first did an elevation to pull out all of the Duricrust capping. Then they looked at aster for all the iron-rich areas for laterite, and of course field mapping. And so here's some examples of truncated profiles. So here's a full profile. Let's see what we've got. Humus-rich soils. Again, that A soil just never gets credit. There's that A soil, there's some pissoliths and a Duricrust, massive Duricrust, mottled clay zone. Okay, well, we know that's our groundwater table here. And this project area obviously had laterite and then moved into a drier environment and formed a Duricrust. So here you can see a truncated profile where the top's been removed. I wanted to briefly talk about copper soil geochemistry. And last year I had the pleasure of working down in Zambia in the African copper belt. And these copper deposits are huge, they're enormous. So here's Ivanhoe's Kamoa and Kakula copper mines. Look at this, is 20 kilometers of mineralization. It's actually like, these are huge sheets of mineralization, stratiform copper. These deposits are so large that when you do soil sampling in this environment, you have really wide space soil lines. Look at that, like a kilometer apart for your soil lines. And for me, coming from gold exploration, I thought that was really remarkable. And your sample spacing can be up to 400 meters apart, and you'll still catch one of these giants. This is the part I really wanted to get across, and this is sort of cutting edge information about titanium, in particular hydrothermal titanium. So titanium is a really beautiful mineral. Here you can see little wedge shapes on them, little tight corners. Here's some nice wedge shapes of titanite. Titanite, hydrothermal titanite, is a great pathfinder for mineral deposits, including orogenic gold and copper gold porphyries, as well as these stratiform copper deposits. And why? Well, first off, titanium forms hydrothermal events at the expense of biotite or magnetite during this albertization event. Now, in soil geochemistry and in your B soils, titanite is a residual mineral. So it doesn't get washed away very far, and it stays within that laterite. So if you get your B soil and you have elevated titanium, that can be super exciting. And there are ways of examining the titanium to see whether it's hydrothermal or not. And you can follow up by looking at these references. Because titanium can form at the expense of magnetite, you get demagnetization of your deposit. So if you have titanium plus copper with a mag low, that could be a good drill target. And also I should say that the titanite then in the regolith converts to anatase. So it's not titanite, but that titanium remains in place in the laterite soil. Termite mounds. termite mounds, you may have heard of termite mound sampling and wondered what's the merit of it. Well, termites sample from the B laterite soil. And why? Because it's clay rich and they need clay to make the mud, to make the mounds. But to keep those mounds sturdy and steady and standing up, they need the resistate minerals that are in the B laterite. And here you can see minerals like quartz, ilmenite. So yes, you can sample termite mounds, especially if you're in a project area where your regolith is so thick, it's really hard to reach your B soil horizon, where you have thick cover to get through. Then yeah, you can sample termite mounds. They're equivalent to, but of course you want to note that they are from termite samples. While we're on the creatures, molehills can be quite enlightening as well. So here you are in the field on your project area and you notice these molehills. Well, look up, well, you can see also some termite mounds here. When you look up close, there are fragments in the molehills. These fragments come from either the stone line or the base of the laterite. So imagine this mole, he's going underground and he doesn't want to be in the A soil that's too close to surface. It's hot, it's friable, it's collapsing on him. He's going to dig in that laterite because the laterite's clay rich and holds up the cavity of the tunnel for it to live in. But then it comes across these fragments. Damn, I don't want these fragments in my face, and it pushes them up to surface into these mounds. These are the ejecta. This is the stuff the mole didn't want in his home. And this is awesome for us as geologists because if you don't have outcrop, you can actually see what your underlying bedrock is by looking at the molehill fragments. And I tested this out by doing a soil pit next to them and finding identical fragments, of course, within the soil pit in the laterite. Lastly, I'm going to be covering artisanal mining of the Supergene gold. How are we doing for time, Jessica? We're good? Hang on. That looks pretty good.
It's yeah, we'll try and get into the discussion soon, but yeah, it's all good.
Okay, I've got about 5 minutes in here.
Right.
So if we look at, awesome, thank you. If we look at artisanal mining, with the increase of gold price over the last few decades, artisanal mining has been on the rise, and it's mostly and often an illegal activity, but the miners are men and women who are trying to make a living as well. And they're targeting this pure, high purity supergene gold that can be gold dust, little nuggets, or huge nuggets. And if we look here at parts of the Amazonia, laterite gold mining and alluvial gold mining and primary gold mining, they can all occur right close together because they're all related. They're all part of that same source. So here's some images of alluvial mining. This is really small scale. It's a man just panning in the river, or a group of men that are going to shovel the gravel over a sluice, or a small team that's got a dredge and scuba divers, and they're going to go and dredge along the bottom of the river. These are all smaller forms of alluvial mining. But you can get really large scale, quite destructive hydraulic alluvial mining. And you can get very large scale laterite mining. So let's spend a few minutes on this slide. This is in the Amazon jungle. This is hydraulic mining. So here the miners are arriving with their big hoses. And hydraulic means that they're using those hoses to hose down the very soft saprolite laterite contact, which is where that supergene gold sits. And this is just so beautiful. This is a model. This is an exact copy of one of these models, but perfect gold. And so what happens is if you have a gold deposit sitting here in the rock, that gold is remobilized. And when these models precipitate, the hematite or the goethite will co-precipitate that gold. And the reason I'm mentioning these sites is that you should go and investigate them, because whether it is the hydraulic mining or whether it's laterite mining is really important, because in this case, you're sitting right within that mushroom dispersal halo. You're so close to that primary source here. This has not been abraded. This is a solid model. So you're very close to the source. You can see all the models here in the foreground as well. The destruction caused by the gold miners can be viewed over time. For those of you who don't know, when you're looking at Google Earth, you can click on that little time down there, and then it gives you the chance to move this bar back and forth, and you can actually go back in time. So for your project area, you can review how it's evolved over time. You can also have primary gold artisanal mining, and how to recognize that in satellite imagery. We can see more permanent housing, and you can see sulfide hard rock piles brought to surface that are quite characteristic. Can you spot the gold trends in there? Here we go. So this is a good example of how artisanal mining, if you can investigate it, you can get a lot of information that can help you vector into your main deposit. So one last quick quiz to see if everybody's paying a lot of attention. 2 sets of soil samples. What's your A soil, what's your B soil, and what type of laterite? So we have here our A soil with those fine hair-like roots, but it's a bit red, that happens. And here's massive laterite, good example of massive laterite. Here's classic A soil and your gravelly laterite with lithic fragments. Last comments, always explain your presence early and hire local guides and translators, and empower local geologists and field technicians. Keep your crew away from local women, and allow for and participate in opening and closing ceremonies with local communities. So those are references you can always refer to later. And congratulations, you just earned yourself 1 professional development hour of informal learning that you can log with your professional association. Thank you very much.